There's this entire world right under our feet, completely hidden from sight. So how do we possibly see what's down there? How can we map out something like an ancient ruin or a dangerous pollutant or even a potential landslide without having to dig up the entire landscape? Well, the answer, it turns out, is to give the Earth a kind of ultrasound.
And I mean, think about it for a second. These are really high-stakes problems, right? Finding a hidden plume of toxic waste could literally save a town's water supply. Mapping an ancient structure could totally rewrite history. And being able to spot a weak, waterlogged layer of soil could prevent a catastrophic landslide. The big challenge is, all of these things are completely invisible from the surface.
Okay, so at first glance, these images probably just look like some kind of abstract art, but they're actually showing us two very real-world scenarios. One of these is a hillside that looks perfectly stable from the surface, and the other is a patch of ground that seems totally normal. But hidden deep inside each one is a potential disaster. These are exactly the kind of mysteries our geophysical detectives need to solve, and by the end of this, you'll know exactly what you're looking at here.
So where do we even start? How does this whole detective story begin? Well, the first, most fundamental clue comes from something you'd never expect: electricity. Yep, just by understanding how a simple electrical current moves through the ground, we can start to build an amazing picture of what's hidden below.
Here's the basic setup, and honestly, it's brilliantly simple. You take 4 small metal stakes, we call them electrodes, and stick them in the ground. 2 of them act like a transmitter, sending a small, controlled electrical current into the earth. The other 2 act like a receiver, and they measure the voltage, or what we call the response, from the ground. It really is just like an ultrasound. You send in a signal, and then you listen for the echo.
Now, the key property we're hunting for here is something called resistivity. It sounds kind of technical, but it's just a way of saying how much a material fights against an electrical current. So, something with really high resistivity, like a dry rock, makes it super hard for electricity to get through. But something with low resistivity, like salty water or wet clay, lets that electricity flow through nice and easy.
And here's the magic, right? This is the key to the whole thing. Every single material underground, whether it's solid granite, porous sand, wet clay, fresh groundwater, or even a nasty plume of chemical pollution, has its own unique resistivity value. It's like an electrical fingerprint. And if we can measure that fingerprint, we can start to figure out exactly what's down there.
And check this out. This chart is basically our Rosetta Stone for reading those fingerprints. This is the aha moment. Just look at the massive difference between something like granite, way up here in the millions, and something like clay, all the way down here between 10 and 100. Or look at the difference between fresh groundwater and superconductive seawater. It's these huge, distinct differences that let us create a really meaningful map of what's going on underground.
All right, so we've got our main clue: resistivity. But just like any good detective, you need the right tools for the job. You wouldn't use a tiny magnifying glass to survey a whole city block, right? Well, geophysicists have different tools too. These tools are really just different ways of arranging those 4 electrodes, and each arrangement acts like a different kind of camera lens, bringing different features into focus.
So let's look at 2 of the most common tools in the toolkit. First, you've got the Venner array. Think of this as your reliable workhorse. It's fantastic for seeing big, flat, horizontal layers, like if you want to map how deep the water table is. Plus, it gives you a really strong, clear signal. On the flip side, you've got something like the dipole-dipole array. This one's a specialist. It's much better at spotting sharp, vertical things, like a hidden fracture in bedrock or maybe an ancient buried wall. The only catch is the signal you get back is a lot weaker.
And this right here is why that choice of lens matters so much. This is the perfect proof. We're looking at the exact same thing underground, a simple rectangular block. Look at the image up top. That's what the broad Venner array sees. Kind of fuzzy, right? Now look at the images below, from the more specialized arrays. The picture is completely different. It's sharper, more focused. The array you choose isn't some minor technical detail. It fundamentally changes what you see.
Okay, so we've picked our lens, we've gone out in the field, we've taken hundreds of measurements. But what we get back, it's not a pretty picture. Not yet anyway. It's raw, distorted data. So the next step is crucial. We have to take that raw data and develop it into a clear, accurate 2D map.
This right here, this is what you get first. It's called a pseudo-section, and you can see why. It's a mess. It's a warped, distorted, blurry version of reality. The shapes look all weird because the image is based on where we took the measurements on the surface, not where the features actually are deep underground. It gives you a hint, sure, but it's a clue that definitely needs to be decoded.
So, how do we clean this up? Well, you know how in every crime show they point at a fuzzy security camera photo and say, "Enhance"? We basically do that, but with a lot more math and powerful software. We take that distorted clue and reconstruct the whole scene.
What happens is these powerful computer programs run what's called an inversion algorithm. It's super complex, but the bottom line is it looks at that distorted pseudosection and mathematically figures out the true picture underground that must have created that specific pattern. And just like that, the blurry clue snaps into focus, revealing a sharp, accurate map of what's really going on.
Okay, we've got the technique, we know the tools, we know how to develop the picture. Now for the fun part. Let's go back to those mysteries from the beginning and see how this technology actually closes the case in the real world.
So, remember that hillside we were worried about? Well, here's what the model showed. See that big blue zone of very low resistivity? That's the smoking gun. It turned out to be a water-saturated layer of clay acting like a lubricant deep inside the hill. This was the potential slip surface. By mapping its exact depth and how far it extended, engineers could finally understand and actually quantify the landslide risk.
And what about that invisible pollution? The results here were just, wow, undeniable. That deep blue blob you're seeing, that's it. That's a highly conductive plume of industrial gunk. It has low resistivity because of all the dissolved salts and chemicals. And the incredible part is they were able to map its size, its depth, and the direction it was moving, all without drilling a single hole or putting a single shovel in the ground.
And for one last example of just how versatile this is, check this out. Engineers were relying on a thick, impermeable layer of clay, that's the blue, low resistivity stuff, to contain some waste. But the survey found these pockets of red, high resistivity spots. It turns out these were gravel-filled holes or windows in that protective clay layer, creating direct pathways for leaks. A critical flaw found completely non-invasively.
So, from predicting natural disasters to tracking down pollution and finding hidden flaws in massive engineering projects, this ultrasound for the Earth has given us this extraordinary new way to see the unseen. It really makes you wonder, now that we have this power to peer beneath the surface with such incredible clarity, what other hidden worlds, what other forgotten histories or looming dangers are just waiting to be discovered?